right, great. So my name is Adam Bouland. I'm a PhD student at MIT advised by Scott Aaronson. And today I'm going to tell you about a recent result that we had, namely that any beam splitter is universal for quantum linear optics. Now, our result can be understood as a simple fact about two-level unitaries without making reference to anything about quantum optics. So recall that a two-level unitary is just a unitary matrix which acts non-trivially on two of the indices while acting as the identity on the remaining indices. So for instance, this matrix is a two-level unitary where the matrix A, B, C, D is acting on indices 1 and 3. All right, so it's well known that by composing two-level unitaries, you can generate any larger unitary matrix you like. So in particular, to generate an M by M unitary matrix, it's necessary and sufficient to take a product of around M squared two-level unitaries. And this was first shown by Reck et al. In 1994. And it also appears, for instance, in Nielsen and Schwang, where they use it as part of the proof that C0 and all single qubit gates form a universal gate set. All right, so this tells you that if you can perform any two-level unitary you like, then you can generate any larger unitary. But what we ask in this talk is, a natural restriction of this. What if you can just perform some subset S of two-level unitaries, but not necessarily all of them? And here, when I say that I have a subset S of two-level unitaries, I'm really talking about the 2x2 matrices that you can apply. And if I assume that if you have a 2x2 matrix in your set S, that you can apply it to whatever indices you want of the larger system and as many times as you want. I'm thinking of this kind of as like a gate set. So for instance, if your set S contains this following 2x2 unitary, you could either apply it, say, to indices 1 and 2 of your system, or you could apply it from index 3 to index 1, or anything similar. All right. So now if you think about this problem, you'll quickly realize that some sets of two-level unitaries obviously won't be able to generate larger and larger unitary matrices. Like, for instance, what if your set S consists of these two matrices? Well, it's pretty clear that when you apply these as two-level unitaries, all you're ever going to get is some subset of like permutation matrices, possibly with phases. So this set of two-level unitaries clearly is not that interesting to us. But what if your set of two-level unitaries contains something like this? Like, what if it contains the Hadamard? Or what if it contains this other strange 2x2 complex matrix? Then it's not really clear what subset of larger matrices these two-level unitaries will be able to generate. So what we ask in our talk is basically, well, are there any interesting sets, and I'm being a bit hand-wavy here, but are there any interesting sets of two-level unitaries which generate more than permutations with phases, but still fail to generate, the whole unitary or the whole orthogonal group? And essentially, the answer to this problem is no. It's not possible to construct such sets. So what we show in particular is if your gate set S contains any two-level unitary which has determinant -1, and all its entries are non-zero, in other words, it does more than just these permutations with phases, then actually, when you apply it as a two-level unitary to a three-dimensional system or higher, it will actually generate all unitary matrices or all orthogonal matrices. And this is a complete classification. This isn't like a statement like with probability 1 over the Haar measure that a two-level unitary has this property. This is a statement that actually all of them have this property. And furthermore, if you just look at the two-level unitary, you can tell exactly what subset of larger transformations it generates. So if the two-level unitary has all real entries, then we can tell that it generates the whole orthogonal group. And if it has if it has any entry which has a complex number in it, then it will generate the whole unitary group. All right, so, and how do we prove such a result? Well, if you only care about this result for real sets of two-level unitaries, then it turns out there's a very nice natural constructive proof which uses some algebraic number theory. Basically, you use algebraic number theory to find a rotation by an irrational multiple of pi that you can generate with these two-level unitaries. But when you try to generalize this to the complex case, it doesn't work. So you need to throw another yellow book at it. And the correct yellow book to throw that is actually representation theory. And essentially the reason that the algebraic number theory proof doesn't work is that SU3, the space of 3 by 3 unitaries, isn't isomorphic to a rotation group. So it's not as simple as just thinking about finding an irrational multiple of pi. You have to do some more work in order to prove a universality result here. All right, so why do we care about this result at all, about two-level unitaries? Well, it turns out that these two-level unitaries correspond very naturally to some objects in quantum optics. So I'll explain what I mean. So if you have a single photon on M modes, then its quantum state is described by a complex vector of length m. And you can write down a basis for its Hilbert states, for its Hilbert space, by just writing strings of length m, where the ith entry tells you how many photons are in that mode. So for instance, these three basis states are the basis states for a Hilbert state of a single photon on 3 modes. And now the sorts of unitary transformations that you can apply to this Hilbert space is given by something called a Beamsplitter. And a Beamsplitter is just a 2 by 2 complex matrix of determinant -1. So that means it can be parameterized by two numbers, alpha and beta, whose norm squared sum to 1. And so that's what happens when you apply a Beamsplitter to just 2 modes. And when you apply it to a larger system, it acts in direct sum with the identity on the remaining modes. So for instance, if you have this Beamsplitter on the left and you apply it to modes 1 and 2, it will generate the following matrix action on your 3-dimensional Hilbert space. So in other words, a Beamsplitter is precisely a 2-level unitary of determinant -1. So what our result says is that if you have any Beamsplitter, you have multiple copies of any Beamsplitter, then you can use those to create, and that Beamsplitter mixes the modes in some way. Then you can use that to create any orthogonal or unitary transformation of a single photon. Yeah, that's the optical rendition of the theorem. All right, so why is quantum optics interesting to us as people interested in quantum information? Well, the place where quantum optical systems get interesting is where you have multiple indistinguishable photons. So let's say you have an optical system with n indistinguishable photons on m modes. Well, then the basis states of its Hilbert space are given analogously to before, where it's a list of integers where the ith integer tells you how many photons are in that mode. So here are the set of basis states for n photons on for 2 photons on 3 modes. But now, a simple counting argument will tell you that the number of such basis states for arbitrary n and m is something like n plus m minus 1 choose n. So in particular, as the number of photons n grows, the dimension of this Hilbert space becomes exponential. So now what unitaries can you perform on this larger Hilbert space? Well, it turns out that the unitaries that you can perform on this large Hilbert space are given as the image of a unitary that you apply to a single photon under some homomorphism phi. And what this tells you is that you can't possibly apply all unitaries to this larger Hilbert space, at least not with passive optical systems. And the reason is, you can see this by just a really simple dimension counting argument, right? I mean, so the space of m by m unitaries is something like m squared. So you can only apply unitaries of polynomial, some space of unitaries of polynomial dimension to this much larger Hilbert space. So we call this small subset of unitaries that you can perform, we call this the linear optical group. And what's interesting about this setup to a computer scientist is that even though you can't perform all unitaries on this larger Hilbert space, these optical systems can still be very difficult to simulate classically. So for instance, Aaronson and Arkhipov recently showed that if you have a linear optical system with a large number of indistinguishable photons, and you run them through some network and then measure in the photon count basis, then you can use these devices to perform something called boson sampling, which isn't efficiently classically simulable unless the polynomial hierarchy collapses. And alternatively, if you allow your optical networks to be adaptive, that is to perform some sort of intermediate measurements and then condition their future beam splitters on the results of those measurements, then the optics are actually capable of universal quantum computing via the KLM protocol. So let's say that we call it a set of beam splitters universal for quantum optics if it generates all unitaries or all orthogonal matrices when acting on a single photon. Then the Solovay-Kitaev theorem tells us that any set of universal optical elements is equivalent to any other. In other words, if you have any set of universal optical elements, then you can either perform boson sampling, in the case that your optical network is non-adaptive, or you can perform the KLM protocol if your optical network is adaptive. So in this optical language, what our result says is any beam splitter which mixes modes is universal for optics on 3 or more modes. We can rephrase this in a computational way to say that, well, if you have multiple copies of any beam splitter, and you consider what sort of optical experiments you can perform with that beam splitter, those optical experiments will either be efficiently classically simulable in the case that your beam splitter simply permute the photons around, or they'll be universal for quantum optics. And by that, I mean either universal for boson sampling or universal for KLM. So this is kind of strange because, a priori, you could have a lot of different outcomes here. Like, for instance, a priori, you could have come up with some set of beam splitters which on larger and larger systems still generate some sort of discrete subset of unitaries, like something like the Clifford group on qubits. And you might be able to, to come up with some sort of interesting classical simulation of that subset. Or you could imagine that, you could come up with some set of beam splitters which can still perform universal optics, but only via some sort of clever encoding or something like that. Or you could imagine that you could have something which is computationally intermediate, like you could have some set of beam splitters that lets you perform, that doesn't let you perform boson sampling, but it still isn't efficiently classically simulable. And what our result says is that none of these things are possible, and that, in other words, it's very difficult. It's very difficult to define a class, a subset of linear optics, which doesn't give rise to universal boson sampling or KLM, and yet which is not efficiently classically simulable. Like it doesn't seem like it's at least by restricting the set of beam splitters available, it's not possible to define kind of an intermediate class in this way. All right, so yeah, our result has one final interpretation of the result before I get to the proof. So as an experimentalist, you might ask, what does this mean to me? Well, here's a slightly strange experimental interpretation. Imagine someone hands you a box of beam splitters, and you have no idea what the parameters of these beam splitters are, but you're promised that they're all identical. They're all made in some same factory in China somewhere or something, and you have no idea what the parameters are, but you do know that it does mix the modes in some way. Then what our result says is that you can use this box of beam splitters to create any optical experiment you like. All right, so I'll now move on to a brief sketch of the proof. So how do you use representation theory to prove some sort of universality result like this? So here's how we do it. So what we do is we consider applying our beam splitter to different pairs of modes. So let's say we first apply the beam splitter to modes 1 and 3, and then to modes 1 and 2. Well, this will generate some unitary action on this 3-mode space. Let's call that R1. And here alpha and beta are just the parameters of the original beam splitter, in case that was unclear. And then we consider applying it to, say, modes 1 and 3, and then 2 and 3 to get another unitary matrix that we have at our disposal. And then we do a third one. So you could come up with more combinations than this, but these 3 matrices will actually suffice for our proof. All right, so now let's consider the set of matrices which are densely generated by products of these matrices R1, R2, and R3. So here, by densely generated, what I mean is we consider all finite products of matrices in the set, and then we take their closure under taking limits. By Solovay-Kitaev theorem, we really only have to care about density. We don't have to care about what you can exactly represent. All right, so now this set of matrices forms, so each of these matrices is an element of SU3. So these set of matrices generate some subgroup of SU3. And furthermore, so these matrices somehow form a representation of some group of SU3. For those of you who don't know representation theory, a representation is just a set of matrices which obey the same multiplication and inversion relations as the group. So what we show is that this representation that we have of the subgroup of SU3, it's actually very special. It's something called a 3-dimensional irreducible representation of this group. And in representation theory, irreducible representations are the fundamental building blocks of all representations of the groups. So our representation is somehow very special. And next we use the fact that our subgroup of SU3 is actually a closed subgroup. This follows immediately from the fact that we only care about the set densely generated and not the set exactly generated. But now there's a really nice fact, is that mathematicians have actually already classified all possible irreducible representations of all closed subgroups of SU3. So this result actually has a long history. So it was first proven in principle by some mathematicians in 1917, but they left part of the classification as an exercise to the reader. And people worked on that exercise in the 60s, and it was finally completed in December of 2013. So yeah, a good moral of the story is that if you're ever reading a pure math paper and something's an exercise to the reader, you should be careful because it might take math around a century to figure it out. But anyways, as of December 2013, we actually know the complete classification. So the subgroups of SU3, well, they are the subgroups of SU2. Then there are 12 exceptional groups. These are kind of the analogs to like the tetrahedral and octahedral and icosahedral subgroups of rotations. There are 2 sets of infinite families. These are kind of generalizations of the cyclic and dihedral subgroups of SO3 rotations. There are 2 disconnected Lie groups, like continuous groups, and there are 4 connected Lie groups. All right, so now I think you might already see how the proof of our theorem works. The way that we prove our theorem is we go through every subgroup, we go through every possible irreducible representation of each subgroup, and we show that our matrices can't possibly generate that particular representation. And therefore, by process of elimination, we've shown that our matrices have to generate all of SU3 or all of SO3. So yeah, this classification is really powerful. So it gets us a lot of leverage here. All right, so yeah, so with my remaining time, I'll try to give you an idea of how you can show that this set of matrices doesn't generate a particular representation of a particular group. And the way you do that is using character tables. All right, so for those of you who haven't seen character tables, don't worry, I'll explain it. I'll explain everything you need to know about them. So a character table describes all possible irreducible representations of a group. So the rows of the character table list the different irreducible representations of the group. And the columns of the character table list the conjugacy classes of the group. And a nice theorem in representation theory of finite groups is that the number of irreducible representations is always equal to the number of conjugacy classes. So in other words, the character table of any finite group is always square. All right, and so what does the table tell you? Well, the entry in the table tells you that under this particular representation, what's the trace of an element of this conjugacy class. Mathematicians call this a character, but in the case of unitary complex representations, it's just a trace. So for instance, this conjugacy class here is the identity. So this tells you that under these 5 representations, the trace of the identity is 1, 3, 3, 4, and 5. In other words, these are the dimensions of the different irreducible representations. All right, so we know that our set of matrices generate a 3-dimensional irreducible representation. So let's show that they can't possibly generate this particular 3-dimensional representation. All right, so here we go. So what we do is we consider taking the traces of the matrices R1, R2, and R3. So they're given here. They're some function of the parameters of your input beam splitter. So now, if these matrices form a representation of this group, then those traces have to fit into that row of the character table, because each of those generators has to correspond to one of the group elements. All right, so in particular, let's look at the trace of rotation 3. So it's minus norm alpha squared plus twice the imaginary part of alpha. Well, if we look at this row of the character table, we can see there aren't any complex numbers there. So from that, we can immediately conclude that if our matrices generate this irrep, then the parameter alpha has to be real. All right? And furthermore, since we know our beam splitter mixes modes, this parameter alpha has to have norm squared strictly between 0 and 1. So what that means, that means that the norm of T3 has to be strictly between 0 and 1. And the only one of these entries of the character table whose norm is strictly between 0 and 1 is this last one, which is turns out to be, I think, 1 minus the golden ratio. All right, great. So we now know that the matrix R3 has to represent this conjugacy class. So now we can explicitly solve for what alpha has to be. Well, alpha has to be plus or minus the square root of 1 minus the golden ratio. Okay, great. So now we plug that into the trace of matrix R1 and R2. And we'll notice that those numbers don't appear anywhere in this row of the character table. Therefore, these matrices can't possibly generate this group. Yeah, QED. So the proof continues similarly. We just do this for every irrep of every group. And eliminating the later irreps can become quite involved, but they all have similar flavors to this sort of proof. All right. So yeah, so in short, we've shown, any beam splitter which mixes modes is universal for linear optics. What sort of future questions could we ask based on this research? Well, one question we can ask is, well, can we extend this result to multi-mode beam splitters? So at the moment, we've shown, any 2-level unitary generates any larger unitary. Could we show that, any 3-level unitary generates any 4x4 matrix or larger? Now, the thing is, our proof techniques don't quite carry through here. And the reason is that although we know the finite subgroups of SU3, as you might guess, we actually haven't classified the finite subgroups of SU4 yet. They're partially known, so the exceptional finite subgroups have been classified, and we know their character tables. But the infinite families of finite subgroups of SU4 are actually still open. You can definitely work on this problem, but using our proof techniques, you'll have to solve some open problems in representation theory first. All right, so the next question you can ask is, can we extend this result to 2-level unitaries of other determinants? I've assumed our 2-level unitaries have determinant -1, so they look like Hadamard. So, if you cared about a particular determinant, like determinant 1 or e to the 2 pi I over 3, you could, in principle, just go through our proof again, go through this giant elimination of every irrep of every subgroup, and then get a universality proof for that. But the problem is that we don't know a generic reason that this would be true for any phase. In particular, if your phase is an irrational multiple, if your determinant is an irrational multiple of pi, some strange things might happen in the proof, essentially because you won't be able to generate special unitary 3x3 matrices. You'll be generating general unitary, U3 elements instead of SU3 elements. And that would make the proof substantially more involved. All right. So next is, can we account for realistic errors? This problem has been solved in theory land, in which every beam splitter is exactly identical to every other one. It would be interesting to prove that that any set of beam splitters which are approximately close to one another are still universal. This I actually think still will be true, but we don't have a proof of this at the moment. All right, and finally, is there a qubit version of this theorem? This theorem is really fundamentally tailored to two-level unitaries, those are not the sorts of gates that you get from tensor products of qubits. So there are some versions of a dichotomy theorem that you can form for, say, 2-qubit gate sets. I'm not sure if they're true, but I'd be happy to discuss them if anyone's interested. All right, and with that, I'll thank you for your time.
Wonderful. We have plenty of time for questions. Yes, yeah.
I was wondering if you thought about this question where, so you call, I think what you call linear optic group, right? It's a particular irreducible representation of the unitary group, right?
Yes.
It's the one corresponding to the, it's in the Schur-Weyl duality of one corresponding to the symmetric group trivial era. That sits inside another irreducible representation of the unitary group, U of D, where D is n plus m minus 1, choose m minus 1, whatever.
That's correct.
So I was wondering if you thought about what gates need to be added to this beam splitter to go to the full unitary group.
Oh.
I think that would be interesting because what you seem to show is that between classical sampling and boson sampling, there's pretty much nothing. That would imply something about boson sampling and full universal quantum computing.
Yeah, that's a great question. I don't have an idea of what gates you would need. So the current constructions, like the KLM protocol, which show that you can have universal quantum optics, the way that they work is they use an encoding of qubits into 2 optical modes, like this dual rail encoding, and they show that you can perform universal operations on this encoded space. And I think that actually is different than performing all unitaries on the exponentially large space. So yeah, I don't know what sorts of operations you'd need to go from there, from the linear optical group all the way up to full unitarity. Yeah.
Thanks.
Okay, any other comments or questions? What do you want? Oh, okay, sure. Don't worry. Okay, in such a case, let's thank Adam and
Thanks.
Okay.